Welcome to lecture 2.6 of the SAGE-based course on Monte Carlo Methods. The topic now is probability. The origins of probability can be traced back to the 17th century. It arose out of the study of gambling and games of chance. Many well-known names associated with probability worked on problems to do with gambling. People like Bernoulli and Pascal did quite a lot of the basic work in this area. Even Newton was persuaded to set down some of his thoughts about a game involving dice. Probability has a language of its own, lots of lingo. So we're going to introduce you to some of the essential terms involving probabilities. An experiment is an activity or procedure that produces distinct or well-defined outcomes. The set of such outcomes is called the sample space of the experiment. The sample space is usually denoted with the symbol capital omega. It's the Greek symbol capital omega that you see here. Let us look at some examples of experiments. Roll a dice experiment. If our experiment is to roll a dice with faces painted red, green, yellow, pink, blue, and black, and find what color the top face is at the end of each roll, then the sample space, capital omega, is going to be the set of outcomes of the colors that show up on the top: red, green, yellow, pink, blue, and black. Another familiar experiment is flip a coin experiment. If our experiment is to flip a coin, where the two faces of the coin can be identified as heads, or H, and tails, or capital T, then we are interested in what face lands up. Then the sample space here, capital omega, is the set of outcomes H and T. Draw a fruit from a fruit bowl experiment. Suppose we have a well-mixed fruit bowl that contains 2 oranges, 3 apples, and 1 lemon. If our experiment is to take a single fruit from the bowl, and the outcome is the type of fruit we take, then what is the sample space for this experiment? Well, the sample space clearly is capital omega is orange, apple, or lemon. So we'll return back to these examples in the sequel. Another important term is event. An event is a subset of the sample space. For example, we could take the event orange, lemon, and that is a subset of our sample space capital omega in the fruit bowl experiment. Probability itself is just a map or a function. Probability simply maps a set of events to a set of numbers. So abstractly, probability is a function that assigns numbers in the range between 0 and 1. The real numbers in the range 0, 1, or the unit interval, is the range of probability. So when probability is denoted by P, and recall that this is the notation for a function. P is a function from the set of events, which are nothing but subsets of our sample space, to the unit interval. But this is not any old mapping, okay? So this probability P, this function, has to satisfy the following axioms. These are things that we hold to be self-evident and true about this function. What are these axioms? The first axiom says, for any event A, the probability of A is a number between 0 and 1. The second axiom says, if capital omega is the sample space, then the probability of the entire sample space, or probability of omega, is 1. The third axiom says if A and B are disjoint, that means if the intersection of A and B is the empty set, then probability of A union B is simply probability of A plus the probability of B, where P of A is just a number in the interval 0, 1, and P of B is another number in the interval 0, 1, and this equality has to be satisfied for disjoint events A and B, sometimes called the addition rule. The final and fourth condition is if you have an infinite sequence of pairwise disjoint events. Okay, here clearly the interesting case would be when the sample space is not a finite set, like in the 3 examples we saw earlier, but something more interesting, like let's say if I keep tossing a coin and count the number of tosses I need before I see my first tail. So this sample space will clearly be 0, 1, 2, 3, or any non-negative integer, because that's the number of times I have to toss the coin until I see the first tail. So that's an interesting and more complicated countably infinite sample space. So in such a situation, what we want is that if you look at an infinite sequence of events, A1, A2, dot, 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 and these events are pairwise disjoint, that means if I take any two elements from this infinite sequence, any two events, then their intersection is empty, then we have to ensure that this probability satisfies this equality. Okay, that means the probability of the countable sequence of pairwise disjoint events, that's what this big symbol here means. The union as I goes from 1 through infinity of AI is nothing but a fancy way of writing A1 union A2 union A3 union dot dot dot, and that whole probability should equal the sum of the probabilities of these individual events. Again, the sigma here simply runs from 1 through infinity, and this is again nothing but the notation for P of A1 plus P of A2 plus P of A3 plus dot dot dot. Now these four axioms or assumptions are motivated by the frequency interpretation of probability. So they don't just come from anywhere. So there is some motivation behind these axioms. The frequency interpretation of probability says that if we repeat an experiment a very large number of times, then the fraction of times that the event A occurs will be close to P of A. More precisely, let capital N of A comma little n denote the number of times the event A occurs in the first n trials of repeating this experiment. Then probability of A has the interpretation that as the number of trials little n go to infinity, it is nothing but the limit of this ratio. This is simply n of A comma n divided by little n, which is nothing but the fraction of times the event A occurs in n trials of the experiment. So that's what P of A should limit to. To think about this, consider what limit as n goes to infinity of n of A comma n over n is. Well, that's nothing but the question of where this particular sequence of fractions is going, right? So the first, if n is 1, we have n of A comma 1 divided by 1. That's the number of times the event A occurs in one trial of the experiment. This is the fraction of times the event A occurs in 2 trials of the experiment and 3 trials and so on. So the question is, where is this fraction going if we keep chasing the sequence? And that is the definition of the limit, right? So let's look at axioms 1, 2, and 3 above more closely from this point of view. For any event A, the probability of A is between 0 and 1. Well, what does that mean? Well, we clearly have the fraction of times the event A happens in n trials. Well, this is going to definitely be a number between 0 and 1, right? Because if A happens every single time in the n trials, then the numerator here will be n, and n over n will be 1. That means A happens always. Or in the other event, if none of the times in the n trials A happened, then the numerator will be 0 over n, which will be the number 0. And any other fraction here will be just a number between 0 and 1. That's all axiom 1 really ensures. Well, axiom 2 basically is saying if omega is the sample space, then the probability of omega is 1. What does this mean? This essentially says something must happen, right? So probability of omega is nothing but the fraction of times some outcome in the sample space, of all possible outcomes in the sample space, something happens. So that will always be n. So n over n is 1. Sure, this is satisfied as well under this interpretation. And the let's just look at the third case. When you have two disjoint events, A and B, that is their intersection is empty, then the fraction of times A union B occurs in n trials has to satisfy the fraction of times A occurs plus the fraction of times B occurs. So we simply divide the left and the right of this equality by n, and we have the third axiom motivated as well. Of course, for the fourth axiom, this simply extends to infinitely many disjoint events under more strict assumptions and the logic under the hood. So axiom 4 is a bit more controversial, right? But here we assume it is part of our axiomatic definition of probability. That's what we assume in this class. We don't go into any philosophical discussions about axiom 4. The main thing is that we take a pragmatic approach. Having axiom 4 helps us make very nice probability models that we'll see in the sequel are very useful to solve real-world problems. Okay. It's a good time to pause the video and go back and read all this slowly and understand what probability is all about. See you in the next video.